So after the last lecture, I'm sure you have gained now a better understanding as to how a PN junction, when forward biased. So this is P region, P side, this is N side. When it is forward biased, how it creates light, it generates light, spontaneous, which is called light emitting. And today I would once again explain briefly though as to how a light emitting diode can be made to work like a diode laser, which has the ability to emit directed coherent light. You see, when the PN junction is forward biased, then the battery pumps hole into the P region and electrons into the N region. So basically what happens, the electrons appear, so this is the conduction band and this is the valence band. So electrons appear in the conduction band and the holes appear in the valence band. Let us, for simplicity, let us consider first just one electron in the conduction band, one hole in the valence band. So as they migrate, as they diffuse into this region, holes are diffusing into the from the P side into this junction, and electrons from the N side, they meet in this depleted region of the junction and annihilate. That means the electron drops down from the conduction band to the valence band and recombines with a hole, and then the electron releases this much energy as it has fallen down from the conduction band to the valence band. This is the excess energy which the electron will release, and in case of a direct band gap semiconductor, this band gap energy, which is delta E, will be converted into a photon. If photon's frequency is nu, then nu becomes equal to delta E, which is the band gap energy by Planck's constant. So this photon will be emitted. Now, if we have to convert this LED into a diode laser, that means first we have to create population. Now for this, there are two processes which is in action here. One is, of course, this recombination of the electrons and holes, which results in the creation of photon. And the other process which is operative is this photon, whose energy exactly matches the band gap energy, and therefore the electrons which are present in this valence band, an electron can absorb this photon and readily climbs up to the conduction band. So the electron comes here and it creates a hole. Now, so recombination of electron and hole results in creation of a photon, and this absorption actually removes a photon from this system. So population inversion will be created if the rate at which recombination creates these photons increases the rate at which the photons are removed through the process of absorption. So if you have to create more photons through recombination. That means you have to pump the electrons in the conduction band and holes in the valence band at a faster rate. Faster you pump them, with increased rate of recombination, more photons will be generated. Then they will be absorbed. So when such a situation has been attained, we will say that the population inversion has been created. Population has been created in this system. So now, if you can integrate this population inverted medium inside a cavity, then of course it will result in amplification of light. Stimulated emission will result in amplification of light, resulting in the emission of a directed beam of coherent. Now, so how do you make a cavity here? See, nature has been kind here, because this is, I have shown here the two-dimensional view. If you see in 3 dimension, then it would look like this. So this is the width of this depleted layer. This is the length, the width. Now, as I said, nature has been kind, because most of the semiconductor material has very high refractive index. For example, gallium arsenide, the most popular semiconductor material for the generation of light, has a refractive index which is 3.6. Compare it with the refractive index of glass, which is usually about 1. So this is much more than this. Therefore, the Fresnel reflection, that is the reflection when light falls, so this is gallium arsenide, and so this is air. So its refractive index is 3.6. This is what. So the Fresnel reflection is the reflection, normal angle of incidence. The percentage of light that reflects back is the Fresnel reflection, which in this particular case can be shown to be approximately 35%. That means if 100 photons shines onto it, 35 photon will be reflected, and so 65 photons will be transmitted. This will be reflected, this will be transmitted. Therefore, if both these end faces, this and this, if they are clipped to make optically flat surface, then these two end faces themselves can work as the cavity mirror. And the spontaneous emission that will first begin from here, and spontaneous emission, light will be emitted in all possible directions. So some of the photons which will be emitted along this axis will actually seed, will perform as the role of seed photons and initiate stimulated emission. And therefore the light will oscillate back and forth between these two phases. And because already population inversion exists, it will result in amplification of light. But for that, you must understand that gain must exceed the loss. Suppose you have created population inversion in such a way that if you plot the gain of this system here, the gain will have a spectral width. This is frequency and this is gain. And suppose with this transmission loss, that is 65% loss from this phase and also 65% loss from this phase. So the loss line is located somewhere here. This is loss, this is gain. If the gain exceeds loss, then there will be lasing and it will give coherent beam of light that will emerge from these two. This is the laser beam, and it will actually be emitted from both the faces. Because both the end faces will transmit 65% of light and 35% will. So that is basically how a diode laser, a light emitting diode, can be converted to perform as a diode laser. And we have seen that the cleaving the end faces perpendicular to the laser axis therefore allows much of the light created in the junction to be reflected back and forth. This will help meet the threshold condition for lasing in many cases. Now for low gain lasers, when a unidirectional beam of light is required, because this gives out light in both directions. So for low gain lasers, or when a unidirectional laser beam is essential, the reflectivity of the faces can be manipulated by appropriately coating them with dielectric laser. See, when the gain is less, suppose this is your loss line for that 35% loss from both, 65% loss from both ends. Suppose this is the loss line. And suppose this is a weak gain laser. So the gain, suppose, lies here. So under this condition, the lasing condition would not be met. So what you have to do, you have to increase the reflectivity of this, reduce the transmission loss so that the loss line is brought down. So somewhere here. Then only lasing will be effective. So this can be done by manipulating the reflectivity, which can be done by appropriately coating the end faces, that is this faces, with dielectric layer to increase the reflectivity, reduce this transmission loss so that the loss line comes down. So with this knowledge on the working of a diode laser, we can now focus on two specific type of diode, that is a homojunction diode laser and a heterojunction diode. Homojunction diode laser and heterojunction diode. So what is a homojunction diode laser? You see, when the diode is made out of the same type of semiconductor material on both sides of it, the laser is called homojunction diode. That means for homojunction diode laser, both P and N type are made out of the same semiconductor material. Say both are gallium arsenide. This is also gallium arsenide. And suppose this side has been doped in such a way that it is P type and this is N type. And when you bias it forward, then of course the holes that will be pumped into the P side and electrons that will be pumped into the N side, when they diffuse from P to N side and N to P side, they meet in this depleted region, recombine and give out light. Now there is an issue here in case of homojunction diode. So what we do, see, when the diode is forward biased and the current begins to flow, recombination of electron hole pairs sets in across the junction, resulting in the emergence of spontaneously emitted light. So we know that light will be emitted spontaneously. So we do a quick experiment where what we do, we measure the intensity of the light emitted by this junction. suppose this is the P junction, this is the P region, this is the N region, and we actually forward bias it. So then this will emit light in all directions. Although I am showing it in two dimension, light will be emitted all around it over the entire 4 pi second. Now what we do is a small experiment, quick experiment, where we measure the intensity of the light. Will be spontaneously, emission will occur in all directions. So we measure the light that is being emitted, say, along this direction. We place a detector to one end of this PN junction and measure the intensity of light by the detector. Intensity of light as a function of the current which is flowing through this circuit, the function of the current. So when the current is 0, there won't be any emission of light, so light will be 0. Now as you increase the current, the intensity of light, because we are pumping, increasing the current means you are pumping more electrons and holes to the respective sides. So the current will begin to increase. It will increase until at a value of particular value of current, suddenly there will be dramatic rise of this intensity of light. That means at this value of current, you have created population inversion. So stimulated emission has set in and the light is now being emitted, light has been amplified, and you have emission of a laser, directed beam of light. That is, suddenly the intensity of light has shown a dramatic rise. Now this value of current is called threshold current for the emission of laser, for the onset of lasing. So this is the threshold value of current at which population has been, inversion has been created and setting up the process of lasing. The intensity of light gradually increases. This monotonous rise in the intensity of light continues until the current reaches a critical value, when it exhibits a dramatic rise, revealing the onset of lasing. Now the value of the current at which the amplification of light due to stimulated emission begins is called the threshold current for lasing. Now the requirement of this threshold current is exorbitantly high for a homojunction semiconductor. So let us explore as to why the current is so high. Why the requirement of this threshold current is exorbitantly high for a homojunction semiconductor. You see, two sides of the gallium arsenide block are doped, one side for N-type, the other side for P-type. When the diode is forward biased, electrons on the recombine and emit light, that's all very fine. As it is gallium arsenide everywhere, the light can easily escape through both top and bottom faces of the junction. What it means is that both sides gallium arsenide. So the refractive index of this side, I call it mu, both sides are same. Therefore the light which has been created as a result of recombination, if the light has been created here, so as it strikes this, it will just get out. Or if it is created right in the vicinity here, it will just get out. It will just get out because there is no interface. Everywhere refractive index is same. So there is no way that the emitted light can be confined to facilitate the process of lasing. This is one disadvantage of homojunction semiconductor laser, and that there is another great disadvantage. There is nothing to confine the holes and the electrons into the junction to ensure a better rate of recombination. You see, both sides are same. So therefore, band gaps of this side, both are germanium, gallium arsenide. Therefore, the band gap means this is the conduction band, this is the valence band. Conduction band, this is the valence band. So band gap on both sides are same. Therefore, the electrons from this side can easily cross and appear to the onto the other side, and hole from this side also can cross and get into this side. So only if it happens to recombine and get a hole, an electron, get a hole after for dropping back, they will recombine. And many such free carriers, electron and holes, will just move into the other side. And a small fraction of that will eventually recombine, because there is nothing to confine them within this vicinity of the junction. These two factors together contribute to the extremely low electro-optic efficiency of a homojunction laser. This results in dissipation of excessive heat. The heat dissipation basically occurs at the point of contact. Suppose this is the P type and this is N type. Both are of course gallium arsenide. And we have forward bias it. The contacts, that is electrical contacts that has been taken here and here, there is some contact resistance. As the current flows through it, I square R, this is the contact resistance R. I square R is the dissipation of heat. And as we have seen, I is extremely large. We saw that the current, threshold current required is pretty high for creating that condition of population inversion. So I square R can be extremely high, and at this height, this results in dissipation of excessive heat that can easily damage the diode. To prevent this, it is mandatory to cool the device by placing it in a liquid nitrogen bath at 77 degree Kelvin. Even with such cooling, they are incapable. They are capable of operating only in the pulsed mode, as continuous working is impossible to achieve. So what I meant is that even with this cooling, such lasers operate only in pulsed mode. In continuous mode of operation, the heat that is dissipated is extremely high, and therefore it is impossible to operate this homojunction laser to operate in continuous mode. Although historically significant, that means such a laser has been invented, semiconductor laser operation has been invented in such a homojunction diode laser. Other than that, and also it is easy to understand, but these homojunction lasers with their extra baggage of liquid nitrogen bath are actually unsuitable for any practical application. Because for any application, the laser has to also be accompanied by this extra baggage containing this liquid nitrogen bath. So what is the remedy? Remedy is a heterojunction diode. You see, the limitations of homojunction lasers can be overcome if both the light and current carriers are confined within the narrow zone of the junction laser, a seemingly uphill task. So basically what we have to do, we saw that in the operation of this homojunction laser, the main disadvantage was that the light which is produced in the vicinity of the junction would easily pass through, or produced in this side will just travel through. There is nothing to confine the light, and in order to facilitate the lasing. And further, the holes and electrons can easily pass through cross the barrier and travel to the other side, because both these are identical material, gallium arsenide suppose, and they have the same band gap. Therefore, there is nothing to actually confine these charge carriers and make them recombine more effectively within this periphery of the junction where the chance that they will meet. So, if we can confine them, then only the threshold current will become less, because we are able to confine light, and also confinement of these charge carriers will ensure that they combine much more efficiently at a better rate. So that will reduce this current, threshold current. This, of course, is an uphill task. And it is not surprising that the operation of CW diode laser was realized at room temperature more than half a decade after the discovery of lasing in a homojunction diode in the later half of 1962. Homojunction diode laser was invented sometime at the later part of 1962, and although everything was known, the problem is also well known, but to confine them within the vicinity of that junction, PN junction, to reduce the threshold current that is required for lasing was very, very challenging, and it took more than 5 years before the CW operation of a semiconductor laser was achieved sometime in 1968, more than 5 years after the invention of laser. And such operation was achieved in a laser which is known as heterojunction diode. I'll stop here now. In the next class, we will see as to what is the technique, underlying physics, which allowed confinement of both light and the charge carriers in the vicinity of the junction, PN junction, or the diode laser.